Hello and welcome to part 2 of lecture 38, the video version. A reminder of what we're doing. We were looking at a series RLC circuit, which is something that looks like this: a R followed by an L followed by a C, and we were looking at the voltage out as being the voltage across the capacitor there, where this is an AC sinusoidal voltage going in. And if you go through the standard potential divider analysis to get the frequency response of this circuit, you'll end up with Vout equals 1 divided by 1 plus j omega RC plus j omega squared times LC. Now, you can proceed to work out the poles, but that would involve solving a quadratic equation, which is often a bit tiresome. So there is another standard form which will allow you to characterize the system without having to solve the quadratic equation. And that's the standard form 1 over 1 plus j omega divided by q omega naught. The q factor times the resonant frequency plus j omega squared divided by omega naught squared, the resonant frequency squared. And we saw that the resonant frequency is the product of the two poles, but it's also equal to the frequency at which the impedance of the inductor and the impedance of the capacitor cancel out. So at the resonant frequency, the only impedance in the circuit is due to the resistor R. And we have the Q factor as well, which is the gain at the resonant frequency. And you'll notice that the Q factor depends on R, the resistance, but the resonant frequency doesn't. It only depends on L and C. If you go through the algebra to work out the pole frequencies in terms of the resonant frequency and the Q factor, you end up with the two poles, P1 and P2, are omega naught divided by 2q plus or minus the square root of, well, omega naught times the square root of 1 minus 4q squared over 2q. It's a bit tedious to derive that, but it's quite straightforward. You just have to set this equal to 1 over 1 plus j omega over p1 times 1 plus j omega over p2, and then multiply these brackets out, equate the coefficients, and work out what p1 and p2 must be in terms of q and omega naught, and you'll end up with this. Right, we now wanted to start looking at some particular cases of this, and that runs something like this. Yeah, frequency responses. Now, you'll notice that in all of these, the resonant frequency is the same and has been normalized to 1. So for all of these plots, this is the resonant frequency here at 1. What's different is the Q factor. And as we saw, the Q factor is the magnitude of the gain at the resonant frequency. So when Q is 0.1, that means that the gain at the resonant frequency will be minus 20 dBs. Why minus 20? Well, because the gain in dBs would be 20 times log 10 of Vout over Vin, and in this particular case, Vout over Vin is 1/10. Therefore, that would be 20 log 10 of 1 over 10, which is minus 20 dB. So we're 20 dB down in the case where Q is 0.1. Equally, when Q is 10, we can be 20 dB up, which you might find initially rather surprising. That suggests that this circuit is providing voltage gain. Around these frequencies, the output voltage, the amplitude of the output voltage, is greater than the amplitude of the voltage being supplied by the voltage source. And yes, it is. This does happen. we'll have a look now at a few particular cases using this formula here, which is the formula for the poles as functions of resonant frequency and Q factor Q. First special case, very small Q factors. If we have very small Q factors, then j omega, this is the frequency of the poles rather, I should probably write it more like this, P1 and P2, is omega naught over 2Q plus or minus omega naught times the square root of 1 minus 4Q squared over 2Q. Right, consider what happens when Q is much, much less than 1. The first pole, P1, that would occur at omega naught over 2Q plus omega naught over 2Q times the square root of 1 minus 4Q squared. If Q is much, much less than 1, I can neglect this term with respect to that 1, and therefore P1 approximately equal to omega naught over 2Q plus omega naught over 2Q. That's just omega naught over Q. What about the second root? Second root, omega naught over 2Q minus omega naught over 2Q times the square root of 1 minus 4Q squared. Right, I can no longer just assume that 4Q squared is small compared to 1, neglect the 4Q squared, because I would end up with 0, and the second pole is not at 0. I could go through a Taylor expansion and expand that to form 1 minus a term in Q squared plus a term in Q to the power of 4 and carry on that way, but there's an easier way. And the easier way to get a good approximation of P2 is to remember that the product of the two poles is the square of the resonant frequency. And we've got a good approximation of the first pole, therefore P2 must be approximately omega naught squared divided by P1, which is omega naught over P1 omega naught P1, omega naught Q rather. I'm trying to do too many lines of algebra at the same time. Let's not do too many lines of algebra at the same time. Omega naught squared over P1. P1 is omega naught over Q, so that's omega naught over Q. That is omega naught squared over omega naught. Omega naught cancels with that. Net result, Q times omega naught. You would get the same result if you did the Taylor expansion of that thing, but I think this is easier. So we have an approximate formula for our two poles. P1 is approximately omega naught over Q. P2 is approximately omega naught times Q. Right, what does that look like when we plot its frequency response? Well, you end up with something like this. Here we have a pole at around 1 kilohertz and another pole at around 100 kilohertz. Q factor is 0.1, the resonant frequency is 10 kilohertz, so that is obeying the approximate formula that we've just worked out over here. The Q factor of 0.1, this is 0.1 times 10 kilohertz, and this is 10 kilohertz divided by 0.1. Otherwise known as 10 kilohertz times 10, 100 kilohertz. The gain at the resonant frequency is quite large because the effect of this pole is quite a long way below the resonant frequency, which means that it's having the chance to roll off the gain quite a lot before you get to the resonant frequency, and we get quite a large loss here at the resonant frequency. Okay, next special case. Q factor of 0.5. This is a particularly interesting one because if I put these into the formula that relates poles to the resonant frequency and the Q factor, I end up with, right, now, if Q is equal to 0.5 in this case, then we end up with 0.5 times 2 is 1. P naught and 1 is just omega naught plus or minus omega naught over 1 times 1 minus 4 times 0.5 squared, which is a quarter. That's just 1 minus 1, which is 0. P naught and 1 omega naught. Both of our poles occur at the same frequency and at the resonant frequency. Now, if I draw a Bode plot, as we've done several times before, we know that the effect of a single pole at its pole frequency is to lower the gain by, to a very good approximation, 3 dB. So we're 3 dB below the low frequency point at the resonant frequency here. But I've got two poles in this system. Both of them are giving me 3 dB of loss at the resonant frequency. Therefore, acting together, I would expect them to give me 6 dBs of loss at the resonant frequency, which is exactly what they do.
Can't see it too well on this graph. The scales are a bit big, but perhaps you could just believe me that with two poles at the same frequency, the loss is 6 dBs at the resonant frequency. And of course, with two poles rolling off at higher frequencies, the roll-off here is at 40 dBs per decade. Both poles contributing 20 dBs per decade to this roll-off. Right, that's about all we have time for in the second YouTube video, so see you in part 3.